Let's take advantage of all this time off during the quarantine fun and excitement that we got going on here to talk a little bit more in depth about basic aerodynamics. Before we really get into the nuts and bolts of the aerodynamics, let's talk a little bit about the atmosphere. All right, so here we have planet Earth, and as we know, surrounding that solid surface of planet Earth is an atmosphere, drawing not to scale. All right, that atmosphere, that's going to be all those gases that are held in close proximity to the surface of the Earth, making all life possible, and most importantly, making aviation possible. Now, let's talk about what makes up that atmosphere. So, Earth's atmosphere, it is approximately 78% nitrogen. So, every breath that you take in, you're inhaling 78% nitrogen. Next is the part that becomes pretty important to us as human beings. We have about 21% oxygen. All right. With that remaining 1% being made up of things like water vapor. If you recall from the weather lecture, it's that small percentage of water vapor that's really responsible for most of the weather on Earth. We also have some argon floating around in there. We have some carbon dioxide. Maybe we got some methane and all the plethora of other gases that are floating around in the atmosphere there. Now that atmosphere, because it is held close to the surface of the Earth with gravity, that atmosphere is going to have weight, or for our case, it's going to have pressure. All right, so basically that atmospheric pressure, it results from the weight of those gases above a certain point. So let's say we have a point at sea level and we have 1 square inch. And that 1 square inch goes from the surface all the way up to the edge of the atmosphere. That 1 square inch column of air is going to have some pressure to it. Now at sea level, static pressure is going to be approximately 14.7 pounds per square inch, or 29.92 inches of mercury, or 1 bar. All right, now as we increase in altitude, as we get further away from the surface, that pressure is going to become less and less. Up here at 18,000 feet, or in aviation speak, flight level 180, we're looking at about half the pressure that we have down at sea level. As we get up to around flight level 400, or 40,000 feet, we're looking at about 19% of the total pressure that we have at the surface. When we start working aerodynamic equations, we're going to be concerned about the ambient static pressure, which is going to be annotated with just a small p. And we're also going to be concerned with the static pressure at sea level, that standard pressure, which is going to be annotated as p to the 0. All right. Now, one thing you'll see often in equations is going to be a ratio that is going to be lowercase delta. Lowercase delta is defined as that ambient static pressure over the standard sea level pressure. All right, so we're not just going to be concerned with the pressure when we're talking about aerodynamics. We're also going to be concerned with the temperature of the atmosphere. All right, now when we refer to the temperature of the atmosphere, we're talking about the absolute temperature of air. So if you guys recall, absolute 0, or 0 degrees Kelvin, equals approximately minus 273 degrees Celsius. So that standard sea level pressure is going to be at 15 degrees Celsius. To convert that to Kelvin, we had 273 degrees, which gives us an absolute temperature of 288. So when we're talking about the aerodynamic equations, T is going to be used to define the ambient air temperature, and T0 is going to be the standard sea level temperature, or 288 Kelvin. One ratio you might see is going to be defined as lowercase theta. Lowercase theta is the ambient temperature of the air over the absolute, the absolute standard sea level temperature. So it's going to be the degrees Celsius plus 273 divided by 288, which is the absolute temperature at sea level. The density of the air is a property arguably of greatest importance in aerodynamics. So the density is the mass of air per cubic feet. So your air at sea level conditions weighs 0.0765 pounds per cubic feet and has a density of 0.002378 slugs per cubic feet. All right, so slugs is just how they're going to define that density. All right, in this case, we're looking at lowercase rho. It's going to equal the ambient air density, whereas rho to 0 equals the standard sea level density. One equation you might see is going to be sigma. It's going to be the ratio of the ambient air density over the standard sea level air density.